Hey everyone, today we're dealing with a very special and intriguing problem, which is the three-body problem. Now, you might have heard of this problem by maybe looking at these random plots or by watching recently the three-body problem film that recently came out. We are going to focus in this video on the physical aspect of things, not the movie one. So let me close that. Now, in mathematics and physics and science in general, they often say that if you have a complex problem, this problem can be broken down into sub-problems, which are simpler. So you have a complex problem, boom, you fracture it into simpler, more manageable problems. But did you know that there is actually the other way around, where you can use simple formulations and simple laws to form a very complex, head-breaking problem? Now, believe it or not, this is actually the case of the three-body problem. It is formulated with a very simple laws that results in a very chaotic, unpredictable system. The end goal of this video is to teach you how you can solve yourself this three-body problem, to understand more about physics, astronomy, chaotic systems, and numerical solutions when it comes to Python, where we will be able to make these simulations you're watching right now. Okay, so that being said, let's go. If you're looking to support the channel and dive deep into Python, make sure to check out my Udemy course, Python, Science and Engineering. Enroll today to advance your STEM career and enhance your technical skills. Now, to really understand what the three-body problem is, now, as everyone would do when facing a problem, is to search on it on Wikipedia. Long story short, you can see here you have these planets, or particles, or objects, let's say, or point masses that are moving. Now, to really understand this problem, I made a small introduction right here saying that, okay, the three-body problem is a classical problem in celestial mechanics. So it is the mechanics of planets, galaxies, and so on, how they interact with each other, that describe the motion of three massive bodies interacting with each other. So the three-body problem, in its essence, is in a way to predict the movement and velocity of planets, a bunch of planets. It can be 2, 3. Here it's the three-body problem, but you also have the two-body problem, the four-body problem, the n-body problem for having n planets. The whole purpose is to predict the trajectory of these planets when they are influenced by other planets. One classical example might include a very famous one. If you have the sun, very nice drawing, and then you have the Earth here and the moon surrounding it. The sun is in a way influencing the Earth rotates around the sun. The moon is also influenced by the Earth as the moon rotates around the Earth. Now, it is often known as an analogy. The three-body problem can be assimilated to the Earth, Moon, Sun problem, where we want to predict the trajectories of the Sun, Earth, and Moon, as well as the velocities at each point in time, giving some initial conditions. As you can see here, the goal is to predict the future positions and velocities. Now, there are some assumptions we have to make in order to solve this problem, saying that, okay, if we have, for example, 3 planets in our system, we only consider 3 planets. For example, in our case here, if you consider the Sun, Moon, and Earth system, we only consider these 3. We don't consider, for example, Jupiter, Mars. We don't consider any of these. It's just these 3 ones. For the sake of simplicity, we can concentrate these planets into point masses. So here you can say that the bodies are treated as point masses, having all their mass concentrated at a single point. And as well, we apply the Newtonian gravity. This is very important since we also have the Einstein perception, where it's curvature of space and time. We will not consider these ones. Solely focusing on Newtonian gravity is described by Newton's law of universal gravitation, which is this one, by the way. If I'm sure you're familiar with this one, saying that, okay, if you have 2 bodies, the force that one body has on the other is proportional to the mass of the bodies and inversely proportional to the distance between them. Okay, now having all of this in mind, let's explain this problem a little bit more in detail. Okay, so say you have a planet right here. Let me call it P1. Another planet right here called P2. By the Newtonian means, we know that this planet will exert a force on this planet, and this planet will exert a force on this one. Now, we know that according to Newton's law, the force of 1 over 2 will be proportional to their masses. So it's m1 and 2, and then divided by the distance between them. If this distance is called r, so it's going to be r squared. Now, this is in a way a more specific law, as you will see in a moment. Now, this was the case when we had only 2 planets. But remember, we are dealing with the three-body problem, so we have actually 3 planets. This would mean that we have 1 planet here, Let's say one here and one here. Now, remember, there is an interaction between all the planets. So this planet right here will have a force applied here and then here. We can call this F1 on 2 and then F1, 3. But then again, this one will have an impact on this one and this one. So we have here and then here. This will be F2 on F1 and F2 on F3. So remember, this would be planet 1, this would be planet 3, and this would be planet 2. Okay, so I'm going to change colors. Let me take yellow. And we also have this planet influencing this one and this one. So we have here a force and here a force. So this is the force that 3 is applying on 1. This is the force that 3 is applying on 2. You can already see that we have 3 bodies with 6 total force applied. Previously we had 2 bodies and 2 forces. Now if we had 4 bodies, we will have a total of 12 forces. Why 12? Because it will be 1, 2, 3 per planet. Since we have 4 planets, it will be 3 times 4, which is 12. But you can already see that the more planets you add, the more complex everything starts to get, which makes sense why this is called problem. When having multiple planets interacting with each other, if you want to do things properly, you can define some sort of coordinate system here called x, y, and z. And then the center of this planet is going to be a vector p2. The center of this one is going to be p1. And the center of this one is going to be p3. Now remember this gravitational law, this one. How do we express it when we have a coordinate system? It's actually very straightforward. For example, let's say that the force that the planet 1 is exerting on 2. So if this is planet 1, we want to look for the force that it is exerting on planet 2. So it's this one here on the red one. It is equal to g. So g here, g is the Newtonian constant of gravitation in some sort of constant to the power of minus 11 is g. And then it's m1, m2, here nothing changes. But then remember, we had divided by r squared, which represents the distance between these two. But then if you look at it closely, here we have a vector expression, where here we have an amplitude. It is not making any sense. This is because the actual true expression of the gravitational force is expressed not in terms of divided by r squared, but it is divided by the norm of r1, or the p1, so the position of planet 1. This has the position p2, this has the position p1. I didn't mention it, but it's a position in terms of x, y, and z. So this is x2, y2, and then z2. And then same goes here, same goes here. So it's the vector p1 minus the vector p2. So it is the norm. The norm means, for example, if you have a vector a that you want to get the norm, it represents the square root of the x component squared plus the y component squared plus the z component squared. Okay, so this is basically the norm. And we want to have the norm of p1 minus p2, so the norm of p1 minus p2 here would be equivalent to p1x minus p2x squared plus p1y minus p2y squared, and so on and so forth. You get the idea. Okay, so it's p1 minus p2, and we want to look for the norm. But then we cube this norm, and then we do times p1 minus p2 in terms of vectors. You can see that, okay, all of this is a scalar. Now, but this part right here will give the direction to the force, which means that unit-wise, this is equivalent to g m1 m2 divided by r squared, since this is in meter, and this is in meter cubed, and then meter by meter cubed is meter squared. Okay, so very good right here. Okay, so we have this law right here, a general law of the planet I exerting on planet J. It would be this following. So the force that the planet Pi is exerting on planet Pj, so this is the general law that we will apply in this problem, which is the gravitational law between two planets having a coordinate system. Now, it's almost done. This is our first law. So this is our first law or concept that we will use. By the way, this is not the first law of Newton. This is just the first law that we are going to utilize to formulate our problem. Or three-body problem. Let me call it 3BP. Okay, now coming back to the second law of Newton, I'm fairly sure you're familiar with this one, saying that on a particle, the sum of the exterior forces applied on it is equal to the mass times the acceleration. But we know that the acceleration is the derivative of the velocity, and the velocity is the derivative of the position. This would mean that here you'll have dv over dt representing the velocity, but then again it is equal to m. Let's call it p, for instance, where in this case p refers to position, divided by dt squared. So it's the second derivative of the position. Now what would this mean is that the exterior forces applied on some particle is proportional to the second derivative of the position. Now this is very interesting, since what if we use this law right here? So this is the second law to formulate our three-body problem. What if we use this law right here, and then this law right here, and then we apply them to this system of three bodies right here? Now, you can do it yourself. For example, here, if I apply this on M1, this would mean that, let's say that on P1, we'll just do it for one planet, and I'll show you the resulting system afterwards. So on planet 1, we have the exterior forces is equal to M1, second derivative of the position, P1. And this thing is equal. Now, what are the external forces? So this one, let me do it like this, on 1. What are these forces that are applied on 1? If you go back here to this problem, you see that it is F2 over 1 and F3 over 1. So we know that this is equal F2 over 1 plus F3 over 1. Okay, but then we know that F2 over 1 and F3 over 1 can be determined by using the gravitational law of Newton, by replacing here I, so in this case I is equal to 2, J is equal to 1, and then here I is equal to 3, and then J is equal to 1. You replace the indices here, and then you get at the end that M1. Okay, so at the end you get this expression right here. I just simply replace the indices as we did right here. Now we can clearly see that we can simplify this M1, so this can go with this and then with this. And then we can factor out the G. This would mean that dP1 over dt second derivative is equal to G. Okay, so we have this expression right here. And then you do the same for P2 and P3. You basically do the same thing. At the end, you will get this system right here. You will get here. So what basically we already did all of this mathematical formulation, doing by P1 and then continuing with P2 and P3. We get this system right here. We have on one side a second derivative in terms of position, and on the other side we have P1, P2, so the positions. Now, by looking at this, doesn't this look like a system of differential equations? Why is it a differential equations? Because you have the derivative of a function here that is linked to the actual function. So you have the second derivative of P1 with P1, and then you have the second derivative of P2 with P2 and all. But it is actually a coupled system of differential equations, since in one, you have P2 and P3, and so it's a system of coupled differential equations. Now, by solving this, if you're able to solve this analytically, we're able to solve the three-body problem and find the exact solution at any time given some initial conditions. The problem is we cannot solve this analytically, since it is a second-order coupled nonlinear differential equation, which makes it very hard to do it analytically. This is why we have numerical tools that can help us solve this problem within Python when it comes to solving differential equations numerically. Whether it's Euler method, Runge-Kruger, Newmark method, and so on, you have a lot of methods to do so. Okay, so to recap, we found our system of differential equations that governs this three-body problem. Now, you cannot just go straight ahead and give this to Python and tell him to solve this. First of all, it will get a heart attack. And second of all, whenever you have these type of problems, or when it comes to differential equations in general, now to get meaningful results, you have to give a proper input. And to give a proper input, you have to formulate this problem in a very specific way. What do I mean by that? There are two things you need to do. One that is optional, so the first one is optional, and the second one is necessary. Now let's start with the optional way. Now, you see here, this is our differential equation made up of a system of three equations. You see here the position is in meters, the mass is in kilograms, and the time is in seconds. Now, often when dealing with these type of astrological dimensions, you can see here that G is to the power of -11. The position between planets might be in thousands of kilometers, if not millions of kilometers, and the mass can also be millions of kilograms and so on. So we have very high order magnitude when it comes to these values. Now, one trick we can do to ease off a little bit the process of calculations is to go for a dimensionless version. It says here we might need to rescale our problem to simplify and allowing more stability when it comes to solving our system. This by defining new variables. Okay, so the new variables we define, we have a position, a mass, and a time. Okay, so you might tell me, why didn't we try to dimensionless this constant G? You will see in a moment, it will simplify. And we need to focus on these three. So this is a dimensionless position. It is equal to some sort of position, which is in meter, divided by some characteristic length, which is in meter. Okay, so this is our initial system. And we said that we want to rescale our position divided by some characteristic length. This one will be in meter. and this one will be in meter. But then P, overall P, this one will be dimensionless. So the dimension of this one is nothing. It's just a number. Same goes for the mass. The dimensionless mass will be equal to some sort of mass divided by a characteristic mass, which again has no unit. The dimensionless time is equal to our time t divided by some characteristic time. So here, this one, and this one are characteristic variables. Let's consider a very basic example. Now, let's say we have two planets. For example, we have Earth, and let's say we have the sun, not a planet. We have the sun, a star. Okay. Now, instead of working with the mass of the sun and the mass of the Earth, so let me call this ME and MS, we worked with a new mass, ME prime, which is equal to ME, divided by some characteristic mass. And as well, MS is equal to MS times some characteristic mass. Now, this characteristic mass is in a way to rescale our problem. For example, we can choose, if you choose M is equal to ME, this will result into 1, and this will be MS divided by ME, which is roughly 33,000 bit. That's it, 33,000. Now, instead of working with the mass of the sun and the mass of the Earth, now the mass of the Earth it's almost 6 times 10 to the power of 24, and the sun, you see here there is a relativity. We always compare relatively to Earth. It is about 330,000 times bigger. So I actually made a typo. Let me add 0 right here. There you go. If you want to have the exact number, it is all of this billions kilogram. Now you can imagine this is a very big number. Okay, so this was just an example to showcase what this characteristic mass can be. As well, instead of considering the distance between the Earth and the Sun, which we call r, for example, here, if I say distance between the Earth and the Sun, it is roughly 150 million kilometers. Now, in our case, instead of working with 150 million kilometers, what you are going to do is consider this as our characteristic length. So L is equal to 150 million kilometers, resulting into the relative position between the two planets. So here P prime is going to be equal to P divided by 150 million kilometers, which will result into some sort of dimensionless quantity. For example, instead of P being in the order of 10 to the power of 7, 10 to the power of, 8, it will be roughly between 0, 1 dot something. And this is what we mean by rescaling our problem. Now, if you go ahead here, from this, we express P is equal to L times P prime, we express M is equal to M prime times M, and then you express T is equal to T prime times T. Okay, so this one we can say that it is equal, for example, to the distance between the Earth and the Sun. This, for example, is the mass of the Earth or the mass of the Sun, depending on relatively which planet we want to study the problem. But then there is this T. How do we get this characteristic time? Now, how do we get this? Okay, we know that, for instance, it has the unit of seconds. Okay, so let's explore a little bit the laws we have. We have this law, for instance, and we have this one. Let me write them down. We know that the sum of the exterior forces is equal to m times a, the acceleration, which is equal to g, and then m1, m2, divided by r squared. Let me just write it in this quick manner. For instance, let's forget about this term right here, and let's focus only on this. We have a mass times an acceleration is equal to g, m1, m2 divided by r. Now let's focus only on the units of this expression. So we have something in kilograms, and then an acceleration is equal to something in meters divided by something in seconds squared. This is equal to the unit of g, and to see the unit of g. Okay, so if I go back to the wiki site we just saw, scroll down all the way down here. Okay, you can see here that g is the Newtonian constant for gravitation. Yeah, it is meter cubed by kilogram by second squared. So it is meter cubed by kilogram by second squared. Okay, and then here m1 times m2 is kilogram squared divided by r squared, which is meter squared. Now all of this is the unit of g, so this is g. Let me make this as a g in red. We will not simplify the things that are within these braces. You will see in a moment why. Let's simplify the rest. So we have here kilogram simplifies with this kilogram squared. If I put this one on this side and I put this one on the other side, we'll find that we have a second squared is equal to a meter cubed times the inverse of some kilogram. Okay, and all of this is times 1 over this expression. So let me write it 1 over g in red. Here, we're speaking in terms of units. Let's say now that we speak in terms of characteristic quantities. Let's just state this, for example. Here, second squared would mean that we have some characteristic times squared. It is equal to some sort of distance cubed, for example, our characteristic length, divided by some sort of characteristic mass times 1 over g. Now this would mean that our time, characteristic time, is equal to the square root of L3 divided by m times g. Okay, and this would mean that is equal to, remember it's this one, it's here, okay, it's t divided by this, which means it is the square root of mg divided by L3. Now you will see that this applies since here analyze the units within this. We have kilogram divided by meter cubed, and the unit of g is meter cubed by kilogram by seconds. So this one right here, by kilogram by second squared. We simplify this, and this. You will get that we have t prime is equal to t, has 1 over second dimension. T has the dimension of seconds, or the unit of seconds, which means that t, this one, has no units. So basically we made the time into a dimensionless quantity. This is all that is here explained, as you can see here. So in a way we will replace these ones in our system of equations. So this one, I'll let you do it yourself. It is very straightforward. You go from this expression, you basically replace everything. You simplify here, you see that g will be simplified. You have L divided by L3, which will also be simplified. This one, and this one. And you will be left with m3 divided by m characteristic, which corresponds here, as you will see, to our characteristic mass. I didn't change it here, so let me do it quickly. There we go. So we will have this one. Okay, so this is our dimensionless problem. Now remember, what we're doing right here is to properly package our problem to give it to Python so that it can solve it. Now the first thing we did was making our problem dimensionless by replacing these inside of here, resulting into this system. Now the second thing we need to do is to actually transform our problem into this second order. Since there is a second derivative, we have to transform it into a first order. It is very straightforward. All I gotta do is define some functions f1, f2, and f3. If we say that, okay, we have f1, f2, f3, and then if I do here, say that f1 is equal to dp1 over dt, df1 over dt is equal to the second derivative of p1 dt squared. Now this is a little trick you can do in order to transform any type of system of higher order into a system of first order. If you want to learn more about this technique, I recommend you checking this video out. I went in very much detail there and explain everything. At the end, we will be left with this system. Promise, I'm almost done with this theory. We have this system, and we are looking to solve P1, P2, and P3. Where at t prime is equal to 0, we have informations about the initial positions and velocities of the planets in a dimensionless form. So here, I actually forgot to add a prime, but it's pi prime at t prime is equal to 0. We have pi prime of x0, p0, y0. So here, basically what this means, we have the initial position of this planet, and this planet. So p prime 0, p2 prime at t prime is equal to 0, and then p3 prime at t prime is equal to 0. This refers to the initial position of planet 1 in a dimensionless form at the dimensionless time t is equal to 0. Okay, it is very confusing with all this notation, but it is in a way to make things proper. And this index I refers to the planet 1 here. This refers to planet 2, and this refers to planet 3. Now let me just fix this, so it's p prime. There we go, I just added prime here, since we are speaking about dimensionless quantities. And since we have a dimensionless position, we also have some sort of dimensionless velocity. Trust me, it is confusing, I know, but okay. So, having all of this in mind, all of this theory and math and physics in mind, we can finally put all of this knowledge into Python so that it can help us solve this problem. Alright, so we're back. For me it has been 24 hours later. So we left off at the Python implementation, describing the problem as a whole, mathematically, And we said how we have to properly package our problem so that Python can solve it by making it dimensionless and by transforming our system of second order into a system of first order differential equations. In order to solve this problem, it is often said by myself that you have to split it into a 5-step process. First of all, you import all the necessary libraries, you define the initial conditions and constant, you define the system and so on, you solve it numerically, and then you plot the results. Additionally, you can make an animation. Okay, so importing the libraries. We're dealing with numerical computation, so we are going to import NumPy. We import it as NP. Since we want to do plotting, we also are going to import matplotlib, so import.pyplot as plt. Here we have a system of ODEs that we want to solve, and whenever you have a system that you want to solve, you will often use a special library called scipy. Within this library there is a module called integrate, so we import from scipy.integrate a function called, it's from scipy.integrate, import solve IVP, since we're dealing with an initial value problem. Additionally, we can import the time to measure how quick we solved actually our system. Now when you see our system here, you see there is a bunch of constants, for example m3, m1, m2, but you also have an initial position and initial velocity. So we can go ahead, m1 is equal to, m2 is equal to, and m3. We can also have some initial position and some initial velocity. Now I already have a code prepared, which is here, but we will discover this step by step. And the way I define these is the initial position of planet 1, initial position of planet 2, and planet 3. So let me actually copy all of this down. This is in terms of position, and this is in terms of velocity. Now, in order to solve our system of ODEs, we have to actually define it. And the way you can define it is by defining a function called system of ODEs. This function will return something and we will build it step by step. Here, this is our system. You see there is f1, f2, f3. The input of this function is going to be p1, p2, p3 in the dimensionless form. And we return f1, f2, f3, and df1, df2, df3. We know that df1 dt is equal to, and df2 dt is equal to, df3 dt is equal to. Now we gotta define, basically we have to rewrite this expression right here. So it's, let me scroll down, it's m3. Okay, so basically it's m3 times p3 minus p1 divided by the norm. So to define the norm within NumPy, you can use the np.linearalgebra.norm. This basically gives you the norm of a vector. In this case, it's p3 minus p1 cubed, and then plus the second part, which is m2 times all of this. So we basically repeat this for f2 and f3, for f2 and f3. It's basically very straightforward. You just write this in Python. Okay, now having this, we said that, okay, this function will take as input p1, p2, p3, and dp1, dp2, dp3, and it will return f1, f2, f3, and df1, df2, df3. So we know that, for instance, it will return f1, f2, f3, and then df1 dt, df2 dt, and df3 dt. Okay, but now we have a problem, since we see p3, p1, and all are not defined. Now how do we define them? It is often done in Python, is instead of defining these individually, you define a total vector, let's call it S for solution, that contains all of these p1, p2, p3, and dp1, dp2, dp3. This function takes as input here S, and within this S, it will be a vector that contains p1, p2, and p3. We are going to extract everything from this S vector, and then f1, f2, and f3. There is a better way to write this down. Maybe I can do dp1 over dt, and then dp2 over dt, and then dp3 over dt. And then I say that, okay, f1, f2, and f3 are equal to dp1, dp2, and dp3. By the way, if you're not that familiar with the process of solving differential equations numerically in Python, I recommend you checking this video out, where I went in very much detail and I solely focused on that, so that things might be easier for you. Okay, so we are almost done with this function right here. Remember, this is supposed to be our system of ODEs, so this one. Now, remember, this is a temporal problem, and the way this function needs to be written is your first argument here needs to be the time, or space, or whatever, but it needs to be the variable. For instance, since here we have a temporal problem, since we want to predict across time the position and velocities of these planets, the first argument should be the time, the second should be our vector of solutions, this one, and then additionally we can add the masses here as additional arguments, as you will see in a moment, since we use them in our system. Now, after defining the system of ODEs within Python, we gotta solve it. Now, to solve it, there is this function here, solve IVP, that we gotta use. I can start by saying solution is equal to solve IVP. Okay, and this is a very special function since we have to build it step by step, as you would see in the documentation. So this function takes as input, first of all, a function, our system of ODEs, which is this one, this. It also takes tspan, which represents the lower and upper limits of our time spans. We have the method, so this is an optional. Y0 represents the initial conditions, and then teval represents the nodes at which we want to solve our problem. And arguments is additional arguments you are including in this function. For example, in our case, args will be equal to m1, m2, m3. Okay, so let's build this step by step. Our function, which is our system of ODEs, is the system ODEs. We have to define a tspan. Tspan is equal to, we have to define the initial conditions. So y0 is equal to our initial conditions, the points at which we want to evaluate our problem. So teval is equal to, and the arguments is equal. So I think that's basically all we need. The time we are going to solve this is, for example, between here. Let me copy down this directly. We want to start at 0, which is the dimensionless time, remember, and we want to end at dimensionless time 10, for example. And then we want to create time points from 0 to 10 across, for example, 1001 points. So our tspan in this case will be a tuple from start to end. T-evaluate will be at these time points, the ones we define right here. Our arguments as well will be a tuple of m1, m2, and m3. Okay. Now the initial conditions. The initial conditions here have to be in the same format as this vector right here. And then this vector is in a way a vector containing both positions and velocities of the three planets. So this one has an x, y, and z coordinate, this one as well, this one, and all of these basically. So in a way, we had our initial conditions right here. But what we gotta do is write them, like all of these, we gotta write them exactly like this order. One way to achieve this is by creating another array called initial conditions. Okay, it's going to be a NumPy array that contains position 1, position 2, position 3, as well as velocity 1, velocity 2, and velocity 3. Now if I go ahead and run this and show you initial conditions, it's going to be this. This is not a vector, this is a matrix, but I'll show you in a moment. Suppose that we do here y0 is equal to our initial conditions, and let's simply run everything. It should work, but it doesn't, because here you'll see that y0 must be one-dimensional. Since here it is two-dimensional because it is a matrix, and we gotta, in a way, flatten out our vector. If I do here initial conditions and apply the .rabel method, you can see that we successfully flatten it. So one thing I can do is, after defining our initial conditions, I do here .rabel. When we try to print s, so I want to print the vector s. Okay, now let's rerun this. You'll see that, okay, this is our vector s. And from this vector, you want to extract this as the position p1, this as the position p2, this as the position p3, and this as the velocity 1, 2, and 3. So the way to actually do it, and I'm a little bit silly right here, is, okay, so let me actually go ahead and make it as a comment. So we say that p1, p2, p3 is equal to, here, if you see this s vector, this is p1. So this represents all the elements from index 0, 1, 2. Now to do this within Python, you have to specify s from 0 to 3. 3 here is not included, so it's 0, 1, 2. And then again, I do s from 3 to 6. So it's index 3, 4, and 5, which corresponds to this one, 3, 4, and 5, and so on and so forth. Okay, so let me do this. Since s should be a 1D array, so what I can do is an np.array of all of this, and then I do .rabel. Exactly like we did here. Remember, this function takes as input a 1D array, and it should return a 1D array. So this should be working, hopefully. There you go. Now it works. Okay, So let me actually remove all of this. Okay, let me rerun that. Okay, so let me print the solution. If I print this, okay, you see that we have some sort of weird result when printing the solution. What we are interested in is this y. So this y represents the solution of our system. If you want to extract what interests us is, for example, the dimensionless time t, the x, y, and z position of P1, which have the index 0, 1, 2, and then 3, 4, 5, and then 6, 7, 8. And let me print, for example, P1x. You see that this represents all the x positions of the first planet, and so on and so forth. Now, if you want to go ahead and plot, so maybe I can just copy down this straight to win a little bit of time. So here, first we create a figure on axis. This is what we usually do, but since we want to have a 3D plot, we set the subplot keyword argument. So subplot underscore keyword is equal to, we give a dictionary where the key projection is equal to 3D, okay? And then we define our plots with an axis.plot, and we plot the x, y, and z solution for the first planet. We do it in green, and we give a label, for example, of planet 1. I don't need to do this F right here. Having a certain line width, yes, let me actually remove this, and let's run this. You see here is basically the solution of our problem. Now, if I want to add a dot representing the actual planet in itself, I do like this. It's called planet dot is equal to, I want to plot the very last position of this planet. For example, here, in terms of an array, since this axis dot plot, this should be an array, this should be an array, and this should be an array. This means that here we should have an array, here we should have an array, and here we should have an array. Now we want to plot the last element of this solution for x, the last element of this solution for y, and the last element for this solution for z. Now if I go ahead and run this, basically it just adds this little dot, which is very nice to have. Alright, so welcome back everyone. We are at day 3 of me recording this video. Now to go back on some points I didn't mention on the last part of me recording the video. So here, for instance, the initial positions of the planet were just randomly set. Okay, so now for instance, we just randomly put these initial conditions, but you will see that depending on which initial condition we choose, we get very different results. Okay, but let's discuss this a bit later on. Okay, and then here, something that is worth mentioning. I respecify the solution here of our system by getting the result of the solve IVP function. Now here we get a bunch of informations about the message saying the solver successfully reached the end of the integration interval. Success is equal to true, so it worked. Now since we're only interested in this part right here, we can either do solution dot, okay, or we can also specify it as a dictionary, specifying the key of the dictionary solution. So you see we get the same thing. So usually we do a dot y like so. Now I didn't take the time to analyze a little bit the shape of this result. If I type here, so solution.y dot shape, to get the shape of this, 18 rows and 1001 columns. Now 18 rows corresponds to our initial conditions right here. So if I do initial conditions, you see this is a vector of 18 rows, where this is the position x of the first planet, this is the position y, z, and then this is the position x of the second planet, and so on and so forth. So anyway, in this vector right here, it will mean that if we had, for example, 18 rows and 1001 columns per row, it means that, for example, take one row. The first row would represent all the x position of the first planet. The second row represents all the y positions of the first planet, and so on and so forth. So for example, if I do here y and then 0, I get this array. And if I do dot shape, I get 1001. So in a way, y0 here represents the x position of the first planet. If I want to do it like so, now if I do the transpose of this here, now it will mean that the first row contains all the solutions, so the position x, y, z, all, at the dimensionless time t is equal to 0. So this was just a little clarification on why we did it like this. And then we did plot the result, okay, so it's good and all. The real fun aspect and impressive aspect of this three-body problem is when you see actually all the planets moving, is seeing an animation. Now I will show you briefly how we can animate these results. By doing so, let me quickly copy all of this code right here into a regular Python file, because here, till this point, we worked on a Jupyter notebook, but it's often better to see the animations on this file. Okay, so let me do that right here. I copy all of this. Alright, so there we go. I just copied all of the parts. I didn't use the time module, but it doesn't quite matter. I can, for example, if I say here t1 is equal to time dot, and I say that t2 is equal to time.time, and I want to print how much time it took to solve the system. Say that, okay, I make a print statement, solved in t2 minus t3 in seconds. Okay, so let me close. Now if I go ahead and run this code, it's solved in approximately 18 milliseconds, and we get this. Now the advantage of using a regular Python file is that you can move freely looking at with the mouse cursor. For example, I can go ahead here, zoom on this, maybe see what happened here in this region. You see that the planets are moving like this, and so on and so forth. So it's very practical in this case. Now, let's say we want to animate this. And what do I mean by animating? It's to see the evolution of the trajectory of the planet. So you can see how the planets in a way interact with each other. Now there is a way to do it, which I also covered, by the way, on this channel. This channel is all about physics and Python and numerical computation. So it will take time to explain everything in details. Now, since I covered the exact same concept in these two videos, I'll go a little bit quickly, assuming that if you struggled or didn't follow along, you can always check these two videos to be sure to understand fully the problem. Of course, it is optional, but if you want to do it, you're free to do. I've prepared already full working Python file, which does all the animations. So let me copy all of this for now, and I will try to explain, like highlighting the key points when doing the animation. It might seem a little bit challenging when you see it at first like this. So let me delete, for instance, everything that is not necessary. Okay, so I try to simplify as much as I can the problem. Okay, so first of all, to make animations in Python, you gotta use, within Matplotlib, there is another module called animation. And within this and module animation, you gotta import the funcAnimation function. This is a function that you can use in order to make animations within Python. Now, this function takes as input here, if you can see, it takes a figure, it takes some sort of function that updates the data within our figure, some arguments, and so on and so forth. Now, here, the first argument is the figure. Remember here, initially we created a figure on an axis on which we want to draw actually our planets. So we specify this figure as an input. And then it takes as argument an update function. Now this update function is supposed to update the position of our planets. And you'll see here I did x current 1 is equal to p1x underscore solution, and then from 0 to frame plus 1. So it's the same for these ones. So it's exactly the same thing, but just here it's y and here it's z. Now basically what it means. Now, suppose you have, for example, a sine wave. This is a sine wave. Now, the way the principle behind an animation works is you want to draw this point to this point, and then you want to draw this point to this point, so you have this, and then you want to draw till this point, so you have all of this, and then all of this, and then all of that, and then you slowly build the impression that you're making an animation. So you draw from frame is equal to 0 all the way up to frame 10, and then from frame 0 to frame 50, and then from frame 0 to frame 100, so on and so forth. And this gives the impression of having an animation. For example, here, frame will be equal to 1, 2, 3, 10, 100, 1000, and so on. So after doing this, we have to update the data within our plot. To do this, there is a function within this planet plt1, which corresponds to this here. Notice that it's very important to specify here a comma, since if you don't do it, you will get an array. So this, all of this will return an array. But you want to extract the element within this array. We use the dot set data on x current 1 and y current 1 to update the x and y data. Now to update the z data, we say set 3D properties of z current 1, so this one. So this represents the trajectory of our planet. We can do the same thing with the actual planet in itself. Remember this dot right here, so these ones. And then we basically return both our plots. So planet plt1 and planet 1 dot. So this is all about the update function. This specifies the number of frames we want to have. Say we want to have from 0 all the way up to 1001 frames, corresponding to here our actual t points, this one. This is why I did here the length of t points. This corresponds to 1001. This represents the time between each frame in milliseconds, and this split is just some optimization tool that makes the animation go faster. Now if I go ahead and run this code, okay, you'll see that nothing will happen because here I actually have to remove this plt.show and leave it after creating the animation. Okay, so let me run the code. You can see here now you can see that we are only looking at planet 1 moving. This is because we only updated planet 1. Okay, you can see that's very beautiful. Now if you want to update also these two, all I gotta do is copy and paste this, all of this, and specify here p2x solution, p2y solution, and so on and so on. Okay, so basically what I did, I took this block of code, copied and pasted it 2 times, and then changing here the index 2, 2, and then 2. Same goes here, I did it with 3. As well here, we had planet 1, but we want to do it for planet 2 and planet 3, so I basically just I just changed the index here. So planet2 underscore PLT and then planet2 underscore dot. So this is basically what it is here. And then at the end, I return all of these blocks. Okay, now if I go ahead and run this, you'll see that you get this beautiful animation. Now you see, whenever you try to scroll or try to do a different view, you'll see that everything vanishes. Now this is in a way because of this optimization parameter here, blit. Now if I set this blit to false and I rerun the code, you'll see that now I can see them moving while moving as well the mouse. But it's a little bit less fast in this way, but it's still working. Okay, so let me set blit back to true. Okay, so we get now, this animation right here. You can see here, the planets are interacting with each other, and then this one is slowly being attracted back. These one have some sort of dual pattern they have. If I want to see the animation longer, I gotta increase the time end here. Let's say we set it at 20. We gotta increase a little bit more number of time points. If I go ahead and run this, you see that we get this result. You can see here, previously we didn't see the interaction between the green and the blue. Now they're coming back together, but then here at the end, if I increase a little bit more the time, set it to 30. Let me increase here the number of time points. Okay, so you can see here that they're interacting with each other, but then here, you can see here the interaction between these two, whereas planet 1 is slowly getting away. Now let's say we want to increase the speed of the animation. All I gotta do here is just jump every second frame. For example, if I want to jump every second frame, it means that we take frame 0, frame 2, frame 4, frame 6, frame 8, and so on. And you run this, and you'll see that the animation is much faster. Now we can go ahead and play around with these initial conditions right here, and you will see that depending on the initial condition you choose, even if it's just slightly different, you will get totally different results. For instance, I have come up with some interesting initial conditions, which I called here helicopter. You will see in a moment why. So let me actually copy down this. Okay, so I just changed a little bit the initial conditions here. Position 1 is -half 0 0, and then it's half 0 0, and then it's 0 0 half. And I forgot where I got this number from, but here it's 3 4 7 1 1 1, and then here it's -0.1. But however, if I run this code, you'll see what we get. This is why I call it the helicopter. Since you see, like, these two planets, so planet 2 and planet 1, behave in some sort of helicopter manner, you know? Now, there is one thing I can do to improve a little bit the animation. This is what I did in my original code. Here, instead of starting from frame 0 all the way up to frame, I want to only keep, for example, the 100 last frames currently displayed. To achieve this, all I'm going to do is copy down all of this and then replace it like so. Now, basically, we want to have a lower limit frame where it's the maximum between 0 and then here. If I say frame minus 300, this means that we want to have only 300 frames currently displayed, the last 300 frames. And this is just some sort of print message to say how far we are in the animation. It's frame, the current number of frame, divided by the total number of frames in percentage. Okay, and then I say here, from lower frame to frame plus 1. Now if I go ahead and rerun this, you see here we have the progress of this animation, and you only see the 300 last frames being displayed on the screen. You can see here, everything stops. At the end we got an error because I think the planets were colliding with each other and it wasn't making much sense numerically, so everything just exploded. But then let's say here, okay, now what if, we just give a slight velocity of the third planet in the x direction? What will happen? Let's run this, and you'll see we get a totally different solution. Totally different, like it has nothing to do with it. Then we say, okay, what if we give a little smaller velocity? What will then happen? We analyze this result, and then you'll see here, okay, we get some sort of result, but it has nothing to do now. We have both planet, I guess let me rerun that again. You see, it has nothing to do with the previous result. Now here we have both planet blue and green interacting with each other, whereas the planet red is vanishing, in a sense. Let's decrease it even further. We see what will happen. Now we get an even different result. You see here, now they're in a way interacting with each other, and then boom, they just send everyone flying off. This is what I find so amazing with this system right here. It's so chaotic, but in such a beautiful way. You change just slightly the initial conditions, but then you realize how the result is totally different from each other. Let's see what happens if I add another 0. I don't know what will happen. I'll discover it with you. Okay, so you see here, both vanishes as well. Interesting. Now, let's say we give both a velocity in terms of x and y, and you see what happened. Okay, and total different result yet again. Okay, so like I said, back to 0. Let's go back to our helicopter, and let's run this again. You see, this is all the beauty when it comes to Python and trying to solve some systems numerically. Sometimes we cannot understand fully what is happening, why this condition leads to this result, and how changing it slightly can completely alter the result of it. Okay, so we're coming at the end of this video. It did take a little bit time to explain all the concepts, laying down the code, explaining the animations, and finally looking at the result. But I think it was worth the time if at the end we were able to see such beautiful animations and how Planet might interact with each other in such a beautiful way. If you found other very unique initial conditions, please let me know in the comments the result you found. This code will be available in GitHub. I'll try to polish it a little bit more so that you can understand more easily everything we saw. If you enjoyed this video, please be sure to share with other people that might enjoy it. Maybe leaving a like, subscribing, since I'll be trying to make more videos like these. Maybe igniting this little passion for Python and computational engineering. Check out my course if you want to learn how to do this all yourself. There'll be regular discounts and free coupons applied, so you will definitely check this out. That being said, thank you so much for watching, and I see you hopefully in the next video. This has been Yunus, and peace.